This video will review Section 7b on combinations of probabilities. Now last week, Section 7a, we mainly dealt with only one event. In this section, we will be dealing with more than one event. So the first type of combination is called independent events, and two events are considered independent if their total outcome and probabilities remain the same for each event. And the formula for that is just basically multiplying all of the probabilities together. Now on the right hand side, we have examples of independent events. The first example is a fair die. And again, we have 6 numbers on this fair die, 1, 2, 3, 4, 5, and 6. Each number has the same probability of 1/6 of a chance of occurring when you're tossing the fair die. Another example is a coin, which have head or tails. Each side has the same probability of half a chance of occurring when you're tossing this coin. Another example is a child, a boy or a girl. Each gender has the same probability of half a chance of occurring. Another combination is dependent events. So if independent events has the same probabilities for each event, then for dependent events, the total outcome and probabilities will be different for each event. In this case, the formula for both combination will be exactly the same. You multiply all of the events' probabilities to get your total probability. An example of dependent events: probability of selecting 3 face cards in a row and the cards are not returned back to the deck. Now, since the cards are not being returned back to the deck, then your total outcome and probability will change with each event. Hence, it's going to be considered as a dependent event. Another combination is non-overlapping events. Two events are considered non-overlapping if they cannot happen at the same time. The formula for non-overlapping events is just adding up all of the probabilities together. An example, when tossing a coin, you cannot get heads or tails at the same time. Overlapping events is the opposite of non-overlapping. Basically, two events are considered overlapping if they can happen at the same time. And the formula for that is basically you take the first probability of the first event plus the probability of the second event minus the combination of the two. That way, if we subtract the combination of the two events, we will be left with only one or the other. An example is probability of selecting a queen or a club. Since a queen and a club can occur on the same card, then it's considered as an overlapping event. Now, non-overlapping events and overlapping events has the keyword or that will distinguish them from independent and dependent events. And last but not least, there is the probability that an event occurs at least once. And here's the formula. P at least once is equal to 1 minus P naught of A to the nth power. And the n basically represents the number of trials. Okay, let's go ahead and take a look at our Section 7b homework guide. Now, because we are working with fractions quite a bit in probability, a student in one of my classes found a great online calculator that can be used. And the website for that is www.alcula.com/calculators. So if you Google this in the search engine, you should be able to pull up this calculator here. So in this calculator is basically scientific calculator, online scientific calculator that will give you fractions and probabilities formula, permutation, combination, and factorial, which we will be using in section 7C, D, and E. So let's go ahead and take a look at number 1 here. Number 1 says, determine whether the following individual events are independent or dependent. Then find the probability of the combined events. So in this case here, number 1 says rolling 2 5s followed by 1 3 on 3 tosses of a fair die. So in this case here, the first half of the problem, it does not really matter at all. What matters is the number of tosses and the fair die. Now, remember, a fair die is basically an independent event because all of the probability for the numbers, it doesn't matter what numbers they are, will always be 1/6. So probability will always be 1/6. Okay? So again, it's going to be independent since all the probabilities are the same. So I'm going to bubble in A. Now let's go ahead and figure out our probability. So the formula basically is multiplying all the different events. So basically the first toss times the probability of the second toss times the probability of the third toss. And again, all 3 probabilities will be the same. So we have basically 1/6 times 1/6 for the second toss times 1/6 for the third toss. So here, they want your answer as a simplified fraction. So let's go ahead and put that into our online calculator. So we have 1/6 times 1/6 times 1/6 equals. Now, if you notice in this calculator here, it actually gives you the simplified fraction and the decimal form. In this case here, they only want the simplified fraction, so it will be 1/26. So your answer here is 1/216. So then our probability is 1/216. Now let's take a look at number 2. So number 2, again, determine whether this is independent or dependent. So they say the next 7 births be all boys. And again, the gender doesn't matter. A boy or girl, they will always have half a chance. So again, the probability stays the same for each gender. So it is independent again. We're going to go bubble in B this time. And for genders, the probability is half. Now in this case here, we have 7 births. If you recall, if we are multiplying the same number n times, basically we can actually really use exponential form. So instead of writing half 7 times, I'll just take half to the 7th power. In number 1 here, we could have taken 1/6 to the 3rd power and we would have still gotten the same answer. So let's go ahead and see what is 1/2 to the 7th power. So let's clear this. So 1/2. And again, this caret symbol is basically to the power of. Some calculators may have xy or yx. Power of 7. So they want a fraction again, so our answer would be 1 over 128. So 1/2 to the 7th power is 1 over 128. So our probability would be 1 over 128. Now, number 3 here, again, we're determining if it's independent or dependent. It says drawing 3 kings in a row from a deck of cards when the drawn card is not returned. So the fact that the drawn card is not being returned, that means your total outcome and probabilities will be different for each event. So for the first one here, this little one, basically all they want you to do is bubble in dependent. So then there's nothing really to fill out here. In the second event, the second blank, basically we're going to figure out the probability. So in this case, we're going to have to do probability of the first card times probability of your second card times probability of your third card. So your first card, probability of your first card, is equal to the number of kings in the deck of cards. So remember, there are 4 of each card. In this case here, there are 4 kings out of 52. And again, this is your first card is before selecting the first card. I'm sorry, your first probability is before you select your first card. Now, your second probability, this is after you finish selecting your first card. So remember, we're not returning the card back to the deck, so we will only have 3 kings out of 51 cards left. And again, this is after selecting your first card. So then the probability of your third card is after selecting your second card. Again, we're not returning, so we now only have 2 kings out of 50 cards to select from. So after selecting second card. So then now we'll take all 3 probabilities and multiply them together. So we'll have 452 times 3 out of 51 times 2 out of 50. So again, they say they want your answer as a simplified fraction. So 4 out of 52 times 3 out of 51 times 2 out of 50. Let's double check. 51, 50. Okay. So equals our reduced fraction is 1 over 55/25. So 1 over 55/25 is your answer. Okay, let's take a look at number 4. So number 4 here is similar to number 3. It's going to be a dependent event because it says immediately eating 2 red pieces of candy. Now in this case here, when they say 2 red pieces of candy in a row, they do not mean eating 2 pieces at the same time. They mean eating 1 piece at a time, totaling up to 2 pieces. So here they say your bag contains 11 red pieces of candy out of 42 total. So here, because they're immediately eating, that means your probabilities will be changing each time. it's going to be considered as a dependent event. I'm going to go bubble in A here. So then, in other words, we're going to take our first piece times the probability of our second piece. So our first piece, and again, this is before you select your first piece, we had 11 out of 42 pieces of candy. Now, your second piece, this is after you finish eating your first piece. Now we only have 10 out of 41. So in this case, they actually want a decimal instead of a fraction. So decimal round to 3 places. So again, 11 out of 42 times 10 out of 41. So then our decimal answer here, round to 3 places. The 3 is our third place, so we're going to look at the 8. Since 8 is greater than 5, we're going to round that 3 up to 4. So our final answer will be 0.064. So 0.064. 0.064. Number 5 here, it says randomly selecting a 4-person committee consisting entirely of women from a pool of 14 men and 13 women. Now, again, we are determining if it's independent or dependent. So you're going to ask yourself, if you are selecting people to be in your committee, can you reuse the same person? And the answer to this question is no, you cannot reuse the same person. So this is going to be considered as a dependent event. So again, we're going to bubble in dependent. And again, this is for this little one here. So for the second blank, we're going to figure out the probability. So here, probability of your first person times probability of your second person times probability of your third person times probability of your fourth person. Now, before we figure out the probability, remember, probability has to always be out of something. In this case here, out of our total outcome. So our total outcome will be the addition of the men and women here for the group. So your total outcome is equal to 14 plus 13, which is 27. So your first probability, since we only want women, it will be 13 women out of 27 to select from. Now your second person, we already picked the first person. Now we only have 12 out of 26. Third person, we will only have 11 out of 25. And fourth person, we will only have 10 out of 24. So again, they want a decimal, but round to 4 decimal places. So let's take this and put it into the calculator. So again, our first fraction was 13 out of 27 times 12 out of 26 times 11 out of 25 times 10 out of 24 equals. So again, 4 decimal places. So the fourth place is the 7. We're going to look to the right of it. Since 4 is less than 5, the 7 remains the same. So your answer will be 0.0407. So 0.0407. Okay, let's take a look at number 6. So number 6, this time we are determining if it's overlapping or non-overlapping. In this case here, it says drawing either a black 8 or a black 9. Notice here the keyword or. Unlike the other problems, you did not see this keyword there. So you're going to ask yourself, can you have an 8 and a 9 on the same card? The answer is no. So since it's no, it's going to be considered as non-overlapping. And we're going to bubble in A. So for non-overlapping, basically you add the probabilities for each event. So here, probability of a black 8 plus probability of a black 9. Now, there are 2 black suits and a deck of cards. So that means you will have 2 black 8s out of 52 plus 2 black 9s out of 52. And again, it doesn't matter if they say red, it will be also 2 as well. So 2 out of 52 plus 2 out of 52 will be 4 out of 52. And this basically reduces down to 1 over 13. So your probability will be 1 over 13. Now number 7 is basically similar to number 6. So I'm going to skip that. Okay, let's go and take a look at number 8. So number 8 says, determine whether the events described are overlapping or non-overlapping again. So randomly meeting a 6-child family with either exactly 1 girl or exactly 2 girls. Now the key word aside from or is exactly. So you cannot have exactly 1 girl and exactly 2 girls. You can only have one or the other. So again, it's going to be considered as non-overlapping. So here, you're going to take the probability of 1 girl plus the probability of exactly 2 girls. Now, we need to figure out total outcome. And this is similar to our answer in section 7A. Using the multiplication principle rule. So total outcome here, we have 6 children. Each children has 2 choices. So 2 times 2 times 2 times 2, 2 times 2, or 2 to the 6th power. Same will get you the same answer. And this is basically 64. Okay. Now, we do need to sit down and figure out all the combinations for each event. So for the first event of 1 girl, so probability of 1 girl, we have basically the first child being a girl and then the other rest being boys, second child being a girl and the other rest being boys, third child being a girl and the other rest being boys, fourth child being a girl and the other rest being boys, fifth child being a girl and the other rest being boys, and last but not least, the 6th child being a girl. Now, if you notice here, for the 1 child, the 1 children, basically the girl just switches in order. So, first child, second child, third child, fourth child, fifth child, 6th child. So there's a total of 6 combinations out of 64 where there's 1 girl. Now, technically, it doesn't matter if they're talking about 5-child family, 4-child family, 3-child family, 2-child family. Basically, the one gender will just switch orders for each combination. So if it's a 5-child family, then you'll have the girl in the first child, girl in the second, third, fourth, and fifth. So 5 out of 32. For a 4-child family, it will be 4 out of 16. For a 3-child family, it will be 3 out of 8. And for a 2-child family, it will be 2 out of 4. So all it is just switching the position of the single girl. Now, some problem may say boy rather than girl, but it will be the same probability. Now, the 2 girl event is a lot more complicated. So here, let's say your first two child is a girl and the rest are boy. So let's say then your first child is a boy and the second and third child are girl and the rest are boy, and so on and so on, totaling up to actually 15 out of 64. Now for a 5-child family, it will be 10 out of 32. For a 4-child family, it will be 6 out of 16. For a 3-child family, it will be 3 out of 8. And for a 2-child family, it will be 1 out of 4. And again, what I basically did was actually sat down and did all the combinations. That's how I figured out all of the probabilities. So here we're going to go ahead and add the two events. So the event of having a 1 girl, 6 out of 64, plus the event of having a 2 girl, 15 out of 64. That will give us 21 out of 64. And we cannot reduce this probability. It's already reduced. So here, the probability of meeting 1 girl or 2 girl will be 21 out of 64. Okay, so in number 8, I said that I did basically all of the work on figuring out the different combinations for each child family. And what I did was sort of create a little table here showing you the probabilities so that you guys don't have to sit down and figure out all of the different combinations to the different child family. So here I have the number of children, which is 2-child, 3-child, 4-child, 5-child, 6-child family. And here in the middle column, we have probability of exactly 1 girl or exactly 1 boy, depending on which gender they're looking for. And the last column is probability of exactly 2 girls or exactly 2 boys, and again, depending on which gender they're looking for. So basically, here are the different probabilities for the different children family. Same thing with the right-hand side. Okay, let's go and take a look at number 9. So number 9 here says use the at least once rule. So again, the formula for that, if you guys recall, P at least once equals to 1 minus your P naught A to the nth power. So here what we need to figure out is P naught A and N, the number of trials. So they say getting at least 1 head and 8 when tossing 8 fair coins. So our N, the number of trials, is 8. So this guy is our N. N is 8. Now, they always give you P of A in the problem. In this case here, probability of getting heads, which is half. So then the probability of not heads will be 1 minus half, which is just basically also half. So now we figured out P naught A and the N. We can take this and plug it into the at least once rule. Now to shorten out the at least once, I'll just type in P at rather than actually type out the whole wording of at least once. So P at is equal to 1 minus half to the 8th power. Now in this case here, they say type a simplified fraction. So they want a fraction rather than a decimal. So let's see. So again, we're going to do 1 minus half to the 8th power. So our fraction will be 255 out of 256. 255 out of 256. And that is our P at least once. So our probability of at least once is 255 out of 256. Number 10 also asks to use the at least once rule. It says getting rain at least once in 6 days if the probability of rain on each day is about 0.3. So our n here is 6, so n is equal to 6, which is the number of days. Our P of A, in this case here, the probability of getting rain on one day is 0.3. So our probability of not getting any rain is 1 minus this, 1 minus 0.3, which is 0.7. So then our P at least once, so P at is equal to 1 minus our P naught A with 0.7 to the power of n, which is 6. And again, in this place here, they want a decimal, so we're going to round to 3 decimal places. So 1 minus 0.7 to the power of 6. So then we have 0.882, and our third decimal place is 2, so we're going to look to the right of it. Since 3 is less than 5, 2 remains the same, so our final answer will be 0.882. So this is equal to 0.882. In other words, we have about an 88% chance of getting rain at least once in those 6 days. Okay, number 11 is similar to number 9 and 10, so I'm going to skip that. Same thing with number 13 is similar to 9 and 10. I'm going to skip that. Number 12 is similar to the non-overlapping problems of number 6. So I'm going to skip that. So let's take a look at 14 and 15. So 14 and 15 will be dealing with overlapping. That's the only combination that we have not done so far. So here, number 14 says, randomly meeting either a woman or a Republican. And the reason why we can tell that it's overlapping is because you can have an individual who is a woman and a Republican. Since both of them could be at the same time, then it's considered overlapping. So let me actually write down the formula for overlapping. Overlapping has 3 probabilities. Overlapping will be equal to the probability of the first event plus the probability of the second event minus the probability of the combination of the two. So let's go ahead and continue reading. Randomly meeting either a woman or a Republican in a group composed of 50 Democratic men, 20 Republican men, and 30 Democratic women, and 60 Republican women. So again, probabilities always need a total outcome. It has to be out of something. So let's go and figure out our total outcome first. So total outcome, we have 50 plus 20 plus 30 plus 60. This basically is 160. So we have a total of 160 people in this group here. So our first event is the probability of just women. So in this case here, we're going to add up all of the women and put it out of 160. So probability of women will be equal to our 30 Democratic women plus our 60 Republican women. So that's basically about 90 women out of 160 people. Our next event is Republican. So we need to add up all of the Republicans. So we have 20 Republican men plus 60 Republican women. So that's basically 80 Republicans out of 160 people. Now we need to figure out what is the probability of an individual that is a woman and a Republican. So the combination of the two. We have a total of 60 Republican women. This is the combination of women and Republican. So 60 out of 160. So in this case here, we're going to take these three and plug it into the formula. So we're going to add the first two minus the last one. So when we subtract the last one, basically we'll be left with only just women or Republicans, not women and Republicans. So here we'll have, because they're all over the same common denominator, we'll just do 90 plus 80 minus 60 all over 160. So 90 plus 80 minus 60, that will give me 110 over 160. And this basically reduces down to 11 out of 16. So your probability will be 11 out of 16. Now, number 15 is basically another overlapping problem here. It says, let's minimize the top one quick. So number 15 says the data in the table shows the outcome of guilty and not guilty pleas and 1,048 criminal cases. So this 1,048 criminal cases is basically your total outcome. So here, total outcome is equal to 1048. So let's take a look at part A. Part A here says, what is the probability that a randomly selected defendant pleaded guilty or was sent to prison? Now make sure you guys are reading the problems carefully because part B is very similar to part A here. So our first event is all of the guilties, and our second event is all of the sent to prison. And then the third one, so subtracting the combination of the two. So probability of guilty. So all the guilty pleas is in the columns. We have 385 plus 581. So 385 plus 581. So 385 plus 581, it's about 966. So 966 out of 1048 cases pleaded guilty. So now we're going to look for the probability that being sent to prison. So we're going to add up the sent to prison. Now the sent to prisons are in rows here. So it'll be the first row of 385 and 56. So 385 plus 56. Plus 56. You'll end up with 441. So 441 out of 1048 were sent to prison. Now we're going to look at the combination of the two, the probability of guilty and sent to prison. So basically, we want to find out how many people pleaded guilty and was sent to prison. So the number of people who pleaded guilty and was sent to prison was 385. So 385 out of 1048 cases. So again, we're going to take this and plug it into the formula. First event plus second event minus the combination. So again, first number 966 plus second 441 minus the third 385. And this is all out of 1048. So then in this case, they want decimals rather than a fraction, unlike number 14. So let's go ahead and put that into our calculator here. So we can do 966 plus 441 minus 385, all out of 1048 equals. So then our fraction is 511, 524, but our decimal is 0.975 since they only want 3 decimal places. So we're going to look at the 5, and to the right of the 5 is a 1. Again, that's less than 5, so with the 5 stays the same. So our final answer will be 0.975. So 0.975. Now part B is basically exactly the same as part A. The only difference now is not guilty and not sent to prison. So I'm not going to go over it.